Today we are talking about aeroscope, and specifically we're going to take a look at some internal images of an aeroscope unit that have been shared by Timbink on Twitter. I want to say a massive thank you to Felix for sharing these images with the world, showing us what is actually going on in one of DJI's most secretive products. What we're going to do today is take a closer look at the PCBs, talk you through the radio systems that are located in there, and then at the end I'm going to share with you some thoughts on what drones can be picked up, as well as touch a little bit on the massive data breach that's been found about aeroscope data on a recent Amazon server. Now, just before we jump into it, if you find this video useful, please do make sure you are a subscriber to the channel. If you'd like to support the channel, there are links to my Patreon in the description as well. I want to say a massive thank you to all of my patrons for supporting us, and please do make sure you check out the link to Timbink's Twitter as well and thank him for the amazing work he is doing too. Before we start, it's probably a good idea for me to explain exactly what DJI Aeroscope is. It is a device that is available in both a portable or a ground station unit that allows users to track the location of DJI drones. It is sold to both government entities as well as private companies, and those using the device are able to see the location of a DJI drone when it's in range, see its serial number, and see information such as its current location, its home point location, as well as the pilot location. Aeroscope in itself is designed to pick up the signals from DJI drones, but it will also pick up signals from other models as well. And whilst we don't know for sure exactly what other aircraft it would work with, we do believe it will pick up signals from the likes of Autel and Parrot. Now, as I mentioned, Aeroscope isn't available to purchase by general users, but if you are a government agency or a private company with a good enough reason, they will sell you one. You can, though, rent one in the UK if you need to for as little as £750 for 1 week. Now, there's a lot of debate if DJI making a tracking device for their own drones is a good or bad idea. However, for me, the big concern is about what is happening to the data that Aeroscope collects. For instance, there was a recent data breach where there was over 50 gigabytes of data held on an Amazon server that was collected from over 66 Aeroscope devices, and that was left open for people to find. What's a real concern for users is the fact that it does appear to be the case that you can link multiple Aeroscope devices together and create a large web network of reception over many hundreds of miles, allowing you to collect huge amount of data about the movements of people's DJI drones. Next, we're going to jump in and take a closer look at the images that have been shared online, taking a look at what is actually going on under the hood of an Aeroscope device. Now, first of all, there needs to be a massive thank you to Felix, who is also known as Timbink. Timbink is the person who has shared the teardown images of the OcuSync system on Twitter, and he has demystified a lot of what DJI has been doing. Now, if we just take a look at some of the internal images first of all, before we get onto the PCBs, we can see the internal power supplies located here with XT60s as the power is shared around the boards. So you've got the main PSU here, you've got the AC input, and then you've got the antenna inputs down here, as well as some other AC or I/O down there, a power board or a power filter board located there, and another board up here. There is then the back of the main RF board. So you can see there are two boards. They are sandwiched. You can see there's a board here which fits into this one. You can see that there are micro USB connections along here, and then connections on the boards there. And then you can see the antenna connections that go between the two as well, with the large heat sinks that go around the sides. And then you can see another board there. So this has what looks to be a built-in attenuator over here. More I/O, we've got more power input output, as well as some spark protection, and basically the back end of the main RF system. Now, the really interesting area of the Aeroscope system is the main PCB here, which is the RF board. We have both the top and the bottom, and this is where all of the different radio systems are located that the system is capable of receiving. Aeroscope is designed to work with all of DJI's drones. It will work on Wi-Fi, Lightbridge, and OcuSync, and we can see all of those systems located here on the boards. What DJI have actually done is taken each of their RF blocks and simply replicated them on this board into different areas. What we have is 4 individual sections. So you have one here, 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 and here. One side of the PCB is dedicated to 5.8 gigs and one side of the PCB is dedicated to 2.4. And then we have 2 sets of receivers on each of those frequency bands. So whilst it's capable of receiving up to 4 signals, it is receiving up to 2 5.8 gigs or 2 2.4, but then it has an individual receiver for each of the system protocols below that. You can see here, if we zoom in, each of the areas of the system that is going to receive. So for instance here, this area I'm highlighting here is Wi-Fi 5.8 gigs, and if I scroll across over to this side, you can see it's Wi-Fi 2.4 gigs. If we scroll down, that is replicated again at the bottom, Wi-Fi 2.4 and Wi-Fi 5.8. So what DJI have done is basically laid each of the blocks out for each of the systems. We have the Wi-Fi, as I've already said. Above that, we have the light bridge, which is the 5.8 gig with the 2.4 gig over here. And then we have the SDR, which is OcuSync with 5.8 gig on the left and 2.4 gig on the right. What's really interesting about this PCB is there's really nothing new here. What we're seeing is everything we knew that DJI was doing, and I've covered a lot of this in previous videos, for instance, including my video on DJI's OcuSync system. If you haven't seen that, I will put a link to it in the description where I explain the history of OcuSync, where it came from, and you're actually seeing that here on the PCB because we have the Wi-Fi system from Atheros, we then have the Lightbridge system based on the Artisan chipset, and then we have the lead core SDR for OcuSync, and this is exactly the same as we have seen in their consumer drones. Now, just to explain each of these in a bit more detail, as I've said, we have the Wi-Fi, which is based on the Atheros chipset. Basic Wi-Fi setup, nothing particularly special here. You have the chipset, we have some memory, and then we have some power stages over here, and that is replicated in 4 areas of the board. So one there, one there, and then one over here. Above this, we have the Lightbridge system. Now, Lightbridge isn't based on an SDR. It's sort of a hardware radio. It is sort of an SDR, but it's a bit complicated to explain. But it is based on the AR8001 chipset from Artisan, or that is the same company who makes the chipset that is now used in the Avatar HD system from Walksnail. We have seen this chipset coupled with an NXP chipset before in the DJI Inspire 1 and Inspire 2 and any of their Lightbridge based devices alongside the analog devices AD8040 front end chipset. Again, all they have done here is taken that block there for the 5.8 gigs and replicated that over here for the 2.4 gigs. It's exactly the same chipset. The only thing they'll be changing is the front end of it that allows it to receive the different signals. I am a little surprised that they haven't been splitting on it, but the advantage to doing this means that they can receive multiple different drones on multiple different frequencies at the same time. It's not just about not being able to receive the 2 different frequency bands like they do on the drones. It's about having the capability to receive a Lightbridge device on 2.4 gigs or 5 gigs at the same moment in time. Above this, we then have the SDR. Now, this is labeled SDR 5.8 G1, which is 5.8 gig. And then we have the SDR 2.4 G1 located over here. This is based on the lead core chipset. This is the same chipset that we have seen DJI use in the OcuSync 2 system in the Mavic 2 Pro, which is the LC1860C. It is then coupled to some memory, and then we have the IE1000 front end, which is used for the mixing of the input signals. Again, this setup is exactly the same as we have seen in the OcuSync 2 system. What you might be wondering then is, can this receive OcuSync 3 that uses the P1 chipset as we've seen in the DJI Digital FPV system, as well as their newer consumer drones such as the Mavic 3? And the answer to that is yes. Whilst DJI have moved over to the P1 chipset, that P1 chipset is a newer version or a complete custom version of that original lead core chipset. It is capable of receiving OcuSync 3 exactly the same as that P1 chipset can. So DJI can simply update the software to support those newer protocols. It's just that they're now using the P1 chipset in their newer drones rather than the lead core chipset, because the P1 chipset is more of a dedicated specific ASIC rather than it being an off-the-shelf chip like the lead core. I have done quite a big write-up on the DJI P1 chipset. I put it on SUAS News, and it's also on repair.wiki as well, and I think it's also on my blog on RC Groups. And if you're interested in finding out more about that history, I will put a link to that as well in the description next to my video on the OcuSync system. Now, just to lay this out so you can see it a bit easier, we have the green boxes, which is our SDR with the 5.8 gigs on the left and the 2.4 gigs on the right. The red boxes, which is our light bridge, again, 5.8 gigs on the left, 2.4 gigs on the right, and then our Wi-Fi, 5.8 and 2.4 gigs. And what you can then see is DJI have simply replicated that top area on the bottom, giving them the doubling of the capabilities. Overall, there is nothing magical here. It is simply multiple receivers laid out in blocks. We have a total of 12 receivers, 6 on 2.4 gigs, 6 on 5 gigs, 2 for each of the RF systems DJI are using. If we then hop over to the back of the PCB, there isn't a huge amount here to see, but what is interesting is you can see the micro USB inputs for each of the radio systems located here, 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 and here. And this is how DJI is doing the communication between the radio systems and that other board that is located for the control and all of the usual functionality. Taking a look at another PCB that's located inside, there is another receiver. Now, this may be an add-on board giving it some additional receiving capabilities. But what we find here is another lead core LC1860, which again is that chipset used for the SDR or OcuSync. Another memory chip, as well as more IE1000s, and that's coming directly into that RF input. So what we have there is another capability for the SDR. It doesn't say if it's 2.4 or 5 gigs, but it is clear they have another SDR receiver in here capable of receiving OcuSync type signals. We then also down here have an interesting chipset which is called the Da Vinci chipset. This is something I have actually seen before, and it was used in some very old light bridge systems. There's a memory chip down here. I don't know if DJI are using that for RF decoding, but we have seen Da Vinci chipsets before from DJI in their drones, usually used though for video processing. There's then also an ARM chipset over here, which is most likely a SoC with a program running on it. It's just one of their system management ICs. And just flipping over to the other side of that board, you can see we have some spark arresters from the looks of it up here, as well as the additional circuitry on the back of that other SDR. We have, again, some additional memory modules down here and some other sundry chipsets alongside the V-in and battery. It's clear that DJI have the ability to add more receiving or even potentially transmitting capability to the system. We have those 2 SDRs on the main board, and then we have that additional SDR on this PCB as well, meaning it gives them a total of 3 SDRs capability from a receiving point of view. It is possible DJI are using this SDR for transmitting. Why they would want to transmit from the aeroscope device, I don't know, but it is possible that is there for that reason. Could be that DJI actually have a system that communicates between the different devices. So if you did have multiple aeroscope systems on a site, for instance, they could communicate with each other wirelessly rather than communicate with each other over, say, a hardware link. Now, just taking a look at this last image, there is something here very, very interesting. We can see here at the back the PCB that we had a look at. This is the one with the I/O with the 4 receivers, and it has 2 RF inputs. The other side of the PCB was left unpopulated with more I/O for the RF. This board here, though, looks to be the same board. It's just upside down, flipped around, but it has the opposite I/O populated. We can see here the 2 I/Os left unpopulated, which are the 2 from down here, and you have the larger I/O area up here populated. You have these 2 connections, as well as the rest of the I/O for the RF there. We have another 3 receiver block here, 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 and here, and what this looks to be is another board with more receivers on, doubling up what we had from the original board. So rather than there being 12 receivers, there actually being 24 receivers. So rather than there being 2 receivers per system, there's actually 4 receivers per system for the setup that they've got. And then you have that additional receiver or transmitter, depending on what the setup is, on that other I/O board, giving this system a massive amount of capability. What I suspect is DJI have aeroscope configurable. Depending on which model you buy will depend on its receiver capability. You can either have it with 6, 12 or up to 24 receivers, or even more, depending on the model that you choose. Now that is an overview of the DJI aeroscope system. It is nothing particularly special. It is just multiples of the different types of receivers that DJI have used in the past, and it will be their software that is doing the clever bit of taking those signals, identifying the aircraft, decoding the information from the aircraft, such as the GPS position, the home point position, as well as the pilot's position, and using that to provide information to the authorities or whoever has the aeroscope system, because it has been available to purchase privately as well. Now, as for what DJI drones aeroscope can pick up, well, as far as I can see here, it is pretty much everything on their consumer and their professional line. If it's Wi-Fi, OcuSync or Lightbridge, this unit is capable of receiving it. What we do know though is the DJI digital FPV system is not picked up via the aeroscope system. This isn't that it isn't capable of being picked up, i.e. the aeroscope system can't receive the signals. It's just that they are basically ignored by the system as we understand it, because they don't align like they do compared to the consumer drones. The consumer models will have a whole host of information being transmitted along the data link, including, as I've said, the home point position, the position of the pilot, as well as the aircraft's position, its heading, and all of that telemetry data that DJI provide to the pilot. All of that would be being able to be picked up via the aeroscope system. It's also interesting to think that these devices could communicate wirelessly as well. We know OcuSync can transmit up to 10 plus kilometers, and it's realistic to think that DJI could allow these units to be set that far apart and communicate and act almost as a network of devices, creating a grid effect for being able to receive signals over large areas. As it stands today, with regards to the new DJI FPV system that's around the corner, O3 and the Avatar, we don't really know yet if aeroscope is going to pick that up. However, my bet would be actually yes. I think DJI would not make that mistake again like they did with the original FPV system and actually set it so the new system is detected via their aeroscope solution. Now, it is obviously down to each person's personal opinion if aeroscope is a good or a bad thing. It is a receiving system that is capable of receiving signals on all of DJI's radio systems, but it could also pick up signals from other drones as well, from the likes of Autel, Parrot and others. It is a tool that can be used for good, but like any tool, it can also be used for bad as well. And in recent times, we've seen a data breach of a massive amount of data that has been collected by an aeroscope system being left on an open server. Whilst this data wasn't believed to be DJI's themselves, it just goes to show that there is a huge amount of data out there being collected on the movements of people's drones, and that raises serious questions about not only people's privacy who are flying drones, but what that data is going to be used for and what sort of issues that could create for pilots in the future. It's especially concerning when you look at the fact that this data breach consisted of over 54 gigabytes of data collected from 66 aeroscope devices, of which 53 of them were in the USA. These were all under the control of one company, and whilst it wasn't DJI themselves, I don't know what is more concerning. The fact that DJI are willing to sell 66 individual aeroscope devices to one company, or the fact that those companies can actually track people across the globe and collect that much data. It's even more worrying that a company with that many devices would leave all of that data on an open server available for the world to see. This really does raise some serious questions about remote ID and tracking drones in itself, but also DJI's policy on who they actually sell these aeroscope devices to. If you'd like more information on that data breach, again, I will put a link to that story in the description in this video, alongside the link to my video on the P1 chipset and my video on the O3 system. Now, that is it from me on this one. Please do let me know what you think about this in the description. We will all have our thoughts and opinions, but I'm really interested in hearing your thoughts too. Finally, I'd just like to say, if you have found this video interesting, please do consider making sure you're subscribed. And if you'd like to support us to keep making content like this, please do check out the link to my Patreon in the description. It is only through the support of my Patreons am I able to keep making content on this channel and not have to worry about manufacturers who do or don't want to work with us. I want to say a massive thank you to all of the Patreons who've supported us already, and if you'd like to support us to continue to make content like this, please do consider checking it out. Anyway, that's it from me. Stay safe. I'll speak to you soon.